Good afternoon. So I want to talk about momentum. So I've done some demos and some other things that were related to momentum, but we haven't actually talked about what is momentum, how do you define it, how do you calculate it, how do you use it, okay? So as an object has velocity, a massive object has velocity, it has momentum. And as it goes faster and faster, it has momentum. That's a joke. Okay, let's do something for real. Recall from the second law that F net equals ma. Newton did not write this way, okay? He wrote it differently because we know that the acceleration is the time derivative of the velocity, right? So let's assume that the mass is constant. It doesn't have to be, but it'll make the calculation a little bit easier. Most of the things that we do will be constant mass, or all of the things that we do. We can do a sort of classic raindrop problem where a raindrop is falling and it's accreting mass, it's picking up moisture in the air and so forth, but that's for another day. Okay, I can rewrite this as the time derivative of mv. So the time derivative of mv is the same as ma. This quantity, mv, is what we call momentum. We usually give it the letter P. I don't know why, but maybe some of you out there could look it up and figure out why we use P. I'm not sure. So you might say, well, what's the big deal about just multiplying the velocity times the mass? You know, it's just a constant. It is a constant, but it's a special constant. It's the mass of the object. And that quantity, momentum, is very special because in all cases, in every case you can think of, momentum is conserved. Nature always conserves momentum. This particular case we're talking about is linear momentum. Later on we'll get to angular momentum, so objects that are rotating, objects that are moving and rotating, they may have linear momentum and angular momentum. Okay, so momentum is a vector, obviously. Maybe that's not obvious, but velocity is a vector. If I have a vector over here times a scalar, I better have a vector over here. It won't make sense. So this has units of kilogram meters per second. There is no named unit for momentum that I know of. It's just mass times velocity. And let me talk about this conservation of momentum. It is a conserved quantity. So let's say we have any number of objects. I'll just use 3. Here's M1, here's V1 initial, here's M2, here's V2 initial, here's M3, here's V3 initial, okay? And this is our system, all right? When we say that momentum is conserved, we have to think of the entire system, how the objects are interacting with whatever system that might be, okay? So let's say that we take a snapshot of these objects. At some later time, I'm not going to draw all the final velocities, but at some later time, say they come together, they bounce off, and they go their own separate ways, and we take a snapshot. If we look at the total momentum of the system with that initial snapshot and the total momentum of the system after the collision or however they interact, these are not walls. They're not interacting with the walls, okay? They're just interacting with themselves. I'm saying that this is the system, these three objects. So we take that initial snapshot, which is here, and then at some later time, maybe they bounce together, they've gone off, and we look at those three objects at some later time, you can be guaranteed that they will have the exact same momentum. In other words, the sum of the momenta in the beginning will equal the sum of the momenta at the end. So we say that P final is equal to P initial for our system. This is a summation. I'm talking about the sum of the momenta for all the objects. All right? These conserved quantities, as you already know in physics, are very important to us because they give us a way to solve lots of complicated problems. All right. Let me show you another cute little thing since we talked about center of mass. Let's say you have an object, okay, and it's moving along at some velocity v, and let's say the center of mass of the object is about here. All right? It has some big mass m. So the momentum of this object, I'm not including rotations, I'm not talking about angular momentum. So the momentum of this object is equal to big M, V center of mass, okay? Pretty simple calculation. If we know the velocity of the center of mass, we know the mass of the object, we can calculate the momentum. Let's say that along its path, there is an explosive inside this object, and it suddenly blows apart. It explodes, okay? So at some later time, now, this object is, a bunch of pieces that have blown apart, okay? And here's M1, here's M2, here's M3, maybe it has a velocity here. Maybe this one has a little bit of velocity this way. And maybe this one has a velocity in this direction, okay? If you look at the center of mass of this object and you sum up all these masses, you will get the same final momentum. That center of mass of that object will move just as the center of mass, not of this object, but the center of mass of these three objects. If we were to calculate where is the center of mass now, it would move according to this, okay? Likewise, if you sum up all the momenta of these three objects, since it broke into three pieces, that momentum is going to equal this. Momentum would be conserved. All right, there were no external forces acting on the object. Okay, and we'll look at some cases like that. So this leads us to the idea of impulse, the change in momentum. That's something that we'll be interested in. Everything we've talked about so far has pretty much been, a force through a distance, a force acting over some space. We calculate the work and so forth, or simple forces acting on objects. Well, the change in momentum of an object is equal to the integral from T initial to T final the net force acting on the object, dt. Okay? So a force multiplied by a time gives you a change in momentum. All right? I can make this simpler. I know I wrote it as an integral, but I can make this simpler if this force, and I'm going to drop the net, okay, for a constant force, so I can pull that out of the integral. Delta P is equal to F delta T. It's the force times the time. We call this the impulse. Some places you'll see it written as a capital I with a vector. Impulse is a vector. I typically won't do that because I is the moment of inertia, which we'll get to later. But for the impulse, you can have a big force and a small time. That gives you a certain impulse, or a small force and a big time. Those would be the same impulse, except here you may have a large force acting over a short period of time. Here you have a small force acting over a long period of time. That gives you the same change in momentum, which is the impulse, but you have maybe very different forces here. A lot of times I hear on television shows and other places where they're talking about forces, and they talk about impacts and forces, and they really should be talking about impulse. So the impulse does make a difference. So let's look at a problem with some impulse. We'll eventually get to these problems with collisions, objects moving and smashing into one another. I talked about that the other day in the video that I did with the demonstrations. So we'll talk about elastic collisions, perfectly elastic collisions, inelastic collisions, perfectly inelastic collisions, and so forth. So I want to look at a collision with a wall. Here's a stationary wall. Okay? Now I'm going to just look at the impulse. I'm not going to look at the idea of conservation of momentum, because the object's going to be interacting with the wall, which is attached to the earth, which is an enormous amount of mass. And by the way, I mean, you can have an object that has a huge mass and a small velocity, and a small mass or a big velocity. Okay? Those two have the same momentum, but how they interact with other objects may be very different. Okay? Do you want to be hit by a big M with a small v, or a little m with a big V? I don't know. I don't want to be hit with either one, but all right. So let's say that you throw a baseball. Here's an immovable object. We're going to say that it has a large mass. It's attached to the earth. It's not going to move. Here comes a baseball. Okay, it's a big baseball. And the mass of a baseball, I think, is about 145 grams. Since I'm not in class and I don't have the baseball players here to help me, you can correct me if I'm wrong on that, but okay, I think it's about 145 grams. So that's 0.145 kilograms. Okay? Let's say that it has an initial velocity of 15 meters per second. All right? So the baseball comes in, it hits the wall, it bounces off, and now this is a 1D collision, all right? I'm ignoring the parabolic motion due to gravity, so it's a very short motion, comes in 15 meters per second, bounces right off the wall. Let's say it loses a little bit of kinetic energy, the mass doesn't change, and it bounces off the wall at 13 meters per second. Okay? So I lost a little bit of kinetic energy. That's not going to matter as far as kinetic energy for this momentum calculation. Here's what I'm going to calculate. I'm going to calculate the force. The net force acting, I'll calculate the average force on the baseball. So here's the impulse equation, which I can't seem to write. Delta P is equal to, since I'm going to calculate the average force, then it's just F delta T, and I'll remind everyone that that's the average force. I need to know something about delta T. I need to know how fast or how long the baseball interacts with the wall. That makes a difference for the impulse. Remember, the impulse is F delta T. That's the change in momentum. The longer the baseball contacts the wall, the lower the average force. The faster the baseball interacts with the wall, the larger the force. Okay? Because here's the initial momentum, here's the final momentum. So delta P, if I know that, that's some constant. So if I decrease delta T, I must increase F. If I increase delta T, F will decrease. You all know this from experience. Okay? All right, so delta P, as always, when we write delta, we mean P final minus P initial. Make sure that when you're writing these equations that you remember momentum is a vector. This is one dimension. I'm saying it comes in, I drew it down here below this, but it comes in and it bounces off in the same direction. Okay? So let's do the calculation. P final is equal to 0.145 kilograms. That's M. V is equal to, if this is the positive x direction, so I'm going to make that direction positive. Why not? Wouldn't matter if I made it negative, but we usually make to the right positive. It's a right-handed world. That's the mass. The velocity is negative 13 meters per second. That negative means that it's in that direction. P initial is equal to 0.145 kilograms times 15 meters per second. That's the initial momentum that's in that direction. So I'll go ahead and erase the little drawing and we'll calculate the net force, or the average force. Let's talk about a reasonable value for delta T. I don't know, I guess you would have to perform some experiments to figure out what's delta T. Well, delta T is going to be, I'll give it some value. Delta T, let's say about 2 milliseconds. That seems reasonable to me. Maybe it's not. Look it up online. So this is equal to 0.002 seconds. That's 2 milliseconds. So I'm going to do this calculation. Delta P, that's the impulse. That is P final minus P initial. So I get 0.145 kilograms times negative 13 meters per second minus 0.145 kilograms. So I'll go down here times 15 meters per second. And that is equal to, and then I've got to divide, if I'm looking for the average force, that's delta, I've got to divide this by delta T. So I'll divide the entire thing by 0.002 seconds. Notice, I have a negative here. I'm subtracting another quantity. That's going to give me a net negative for the average force. So the average force is equal to, when you do this calculation, I think I do have an answer for that, believe it or not. Negative 2.03 times 10 to the negative 3, not negative 3, times 10 to the 3 newtons. The negative there tells me that this average force was in that direction. That makes sense. Because the baseball interacted with the wall, and that force that propelled it in the opposite direction was negative. That gave me the direction of the force. What would have happened if the ball were not a baseball and bounced off the wall, but something that stuck to the wall? The impulse would be much less. Okay? Because if P final is equal to 0, you don't get those P final and P initial adding up. Okay? So there is a difference in the impulse when you have something bouncing off a wall or something sticking to a wall. All right. You know, this idea of momentum is a direct result of Newton's third law. For every action, there's an equal and opposite reaction. I don't know if you remember that I talked about, say, like a book falling and impacting the earth, that the earth comes up, rises up to meet the book. Okay, you have a force pair. This is the same thing with momentum. When you have a collision with earth, you have a change in momentum of the object and a change in momentum of the earth. However, the earth is enormously massive in comparison to the object, typically. And you get a very, very minute velocity for earth, for that final velocity of earth. So we're going to see how some of these collisions and so forth work next time. And that's about it for today. Have a good weekend. If it is weekend when you're watching this, I hope everyone's well. See you soon.